Now we'll begin talking about some of the different geometric controls geometric tolerances that we have. And the first thing to notice is that whatever you're tolerancing, your geometric tolerance uses a tolerance zone, an imaginary zone within which the features of your part must lie. Today, we are going to talk about flatness. This is a table, by the way, that organizes the various geometric controls by family. And right now we're in the form family. We're looking at flatness. And I want to point out that its tolerance zone is two parallel planes. Not two parallel lines, two parallel planes. We'll look at that in just a second. These are the form controls, and form controls are only about the surface. They're not features of size. You just apply them to one surface. Let's think about controlling flatness as an example. Here's a block. This happens to be metric. Here's a block with a limits tolerance on it. If you made the part at MMC, at maximum material condition, this part would be as big as it could get, and if it were, it'd be like a balloon expanding to fill a space. The part would have to be perfectly flat on both sides. If it were smaller than MMC, you could start to get some flatness error. And if it were the least material size, if it were 10.2, you could have a situation where it was 10.2 all the way across, but it fit inside a 10.6 boundary, and so you could have a bow in the part, a flatness error of 0.4. Different shape errors happen depending on whether it's bowed or bulged or neck down. You can see there are different possibilities. If you want to control the flatness of a surface, you put a feature control frame somehow on the surface. Here it's on an extension line. There's flatness within 0.2 of a millimeter. And what this means is, whatever size this part is, that bottom surface has to lie within two parallel planes that are 0.2 apart. And I've put this in bold because I really want to underscore that the shape of the tolerance zone is two parallel planes, two flat things, like two flat pieces of glass. When we put these controls on our drawing, the form is a refinement of the size, and what that means is the flatness control, in this case, is a smaller tolerance than the size control. So that often happens, that the size can vary up and down by quite a bit, but you need the form, you need the flatness to be more refined, to be a smaller size. Here's a crude example. Let's say you're building a table, a work table, and you want it to be 30 inches high, more or less. You're not too fussy. If it were plus or minus 1 inch, that would be okay. 29, 31 high, that'd be okay. But it's a work table, so you need your surface to be relatively flat. This drawing, I would not call this flat, but this drawing is saying this surface must be flat within a tolerance zone of two parallel planes that are 0.5 apart. So what this drawing is saying is that whatever height your table turns out to be, once it is at that height, there are two parallel planes 0.5 apart within which all the bumps on the surface must lie. This is out of our book, I think. Here's a part, this is also metric. Here's a part that has a size tolerance, plus or minus 0.3, and a flatness tolerance, two parallel planes 0.1 apart. And here in the bottom is what this actual part can look like. So the actual size of the part is allowed to vary from 12.5 plus 0.3 to 12.5 minus 0.3, so it could vary from 12.8 to 12.2. But the bottom surface with the flatness on it, the entire surface must lie within two parallel planes 0.1 apart. That's what that says. Now, nothing about this control is talking about parallelism or anything else like that. It's not saying whether one surface is parallel to another. It's just saying this one surface by itself is flat within these two parallel planes. So here's a drawing with a size tolerance and a flatness control. And this size can vary from big at one end to small at the other end. According to this size tolerance, that's acceptable. Wherever it turns out to be, now our inspector comes along with some kind of measuring tool and verifies that that surface is flat within 0.1. Even if that surface is sloped, that doesn't matter. What matters is it flat? This is a surface control, so you put the feature control frame attached to the surface. And you can do that with a leader line. You can do that with a leader line or by attaching it to an extension line. And notice the box can be on either side of the extension line. Doesn't matter. Here's a part. It's got a size, this is inch, size tolerance of plus or minus 5 thousandths. Well, that means it has a tolerance zone of 10 thousandths, up 5, down 5, so you could have full indicator movement of 10 thousandths. If you add a flatness control, now you can still have a size tolerance that's plus or minus 5, but wherever it turns out to be, the top surface must be flat within two parallel planes that are 3 thousandths apart. And so now the full indicator movement will be a total of 3 thousandths, not 3 thousandths up and down, but within two parallel planes 3 thousandths apart. Surprisingly, flatness is hard to inspect. I will just say that parallelism is the opposite. It's easy, but flatness is hard because the inspector is only allowed to inspect the one surface. They're not allowed to inspect it relative to another surface because that's not on the drawing. So they have to have, one way is some way of figuring out how flat is this surface not relative to anything. So they might use these leveling jacks and take a bunch of trial and error readings, adjust these up and down, run the indicator over the top, see what reading they get, try it again. It's really time consuming. Here they are again. They could put the part up on some kind of supports and run the indicator underneath the part. What they won't be able to do is measure the flatness where the part sits on the blocks, but they could maybe rotate it and do something or other. So this is a way to inspect the flatness of that surface. If a company makes a large quantity of these parts, what they will do is they will make a tool. They'll make a very flat surface plate with a hole in it, and the dial indicator will come up through the hole, and then they will move the part to be inspected back and forth over that hole and watch the indicator reading on that dial indicator. That's probably the easiest way. Here we go. There is another kind of tool that's kind of interesting that you may run into in a shop, in an inspection shop, and it's called an optical flat. And these optical flats have these polarized bands inside them. They come in different degrees of tolerance. They have these polarized bands in them. And when you put your optical flat, your piece of glass, over the part you're inspecting, light comes through that glass and gets bent, and reveals these fringes, these dark lines in the glass. The farther apart the fringes are, the more tipped, the more distance there is. If the fringes are evenly spaced, as you see here, it means we have a flat surface, it's just on an incline. If there's a curve in the part, you'll see those fringe lines curve, or if there's a scratch, you'll actually see the scratch reflected in the fringe lines. And you can actually get quite accurate. Here are some of the kinds of patterns that you can register in these optical flats. And then your inspector will measure how far apart are these fringe lines, and that will tell them how far out of flatness it is. So that's another method.